Welcome to our final discussion of limits, wherein we talk about a few of the other situations that you can run into where you are exposed to a limit and what it is you're supposed to do to deal with those problems. Much like the last time, we are mainly using limits to deal with indeterminate quotients, which is to say quotients where you would otherwise produce a 0 over 0. The three methods you've learned so far are factoring, rationalizing, which would be using the conjugate to remove a root, and then simplifying a rational expression, which mostly just means finding a common denominator and then adding or in some other way simplifying an expression that involves rationals. Today we're going to round out our limit techniques by talking about two more items, namely visually, like drawing them, which is method number one. Okay, so there's a couple of them we're going to draw and experiment with that. And then the major one is here, the substitution strategy, which is a really important idea. Okay, and we'll go through that and exactly what you need, and we'll look at a couple of examples that will help with that. The at the end, the last page here. The last page again has another substitution in it, and then this is a sort of graph with conditions type of question, which is certainly a very common test question that we will look at as well. Okay, and that's basically the summary of today's piece. So, of course, when we are talking about limits in the context of a piecewise function like this one, the question naturally is going to be, does the limit exist where the two functions meet? Right? Because, of course, where the two functions meet is a natural place where the limit might not exist. We know that in a given question, the limit exists almost everywhere. It only doesn't exist, at a very specific location where it's undefined or indeterminate. Or rather, even there, I mean, the limit might exist, but we're only looking for it in one specific place. In a piecewise function like this, many times what you're doing is you are looking for the limit at the so-called joint, which is to say where the two functions meet. Now, if we draw this function, so I'm going to draw it, okay, so again, GeoGebra are really good for drawing piecewise functions. If x is less than 0, draw 1 over, if x is greater than 0, draw 1 over x, otherwise draw 1. Okay, and that's kind of what this graph is, right? 1 over x if it's positive, and 1 if it's not. And just visually inspecting this graph, it's quite easy to tell that would I say that the limit exists here when x approaches 0? I mean, the answer is no, right? I mean, there's two reasons why not. The first reason is that the left-hand limit, right, which exists and is a 1, obviously does not match whatever's happening on the right side. But actually, if we drill into the right side a little further, the right side limit here just doesn't exist at all. Right? What is the right-hand limit in this situation? There is none to speak of. As x approaches 0 from the right, y does not approach a limit. Let's review that, right? F of 1 is not that high. F of 0.1 is a lot higher. F of 0.01 is very high, and so on and so on. The closer I make x to 0, y does not settle on a limit. Y keeps getting larger and larger and larger. This is behavior that we recognize as asymptotic behavior, right? That is the behavior of an asymptote. So when we go to try to analyze this one, again, we can draw this. Now again, I'm notoriously bad at drawing on this thing, so apologies in advance. But we have a straight line here, and let's put a filled-in circle at the end, right, which indicates that this line exists here at the y value of 1 up until 0 and including 0. Now after 0, we're supposed to draw 1 over x, which, as you might know, goes through 1, 1, and then sort of goes down to a horizontal asymptote there, and then comes up towards a vertical asymptote here, right? So sort of. I know I'm not doing a great job at this, but you get the idea. Now, if we were to talk about the left-hand limit here, which remember is the limit as x approaches 0 from the left, right, of f of x, this is no problem. It exists and it approaches 1. If we wanted to talk about the right-hand limit, which is the limit as x approaches 0 from the right of f of x, we have to conclude it does not exist because there is no value that y goes toward from that side. Y just keeps getting higher and higher and higher. It is unlimited. It has no limit. So there are two ways you could answer this question, but let's focus on the first one. Since RHL does not exist, the limit does not exist. Okay, so this is the first sort of type of problem that you can get, right? You can get a piecewise function where the two sides do not connect. Now in this case, not only do they not connect, but one side doesn't even have a limit at all. And the conclusion is, of course, if any limit rule is broken, the limit does not exist. So remember, for a limit to exist, it must exist on the right, it must exist on the left, and the two sides must agree, and that test is failed here as the right-hand limit does not exist in the first place. Now, for this one, right, what is the limit as x approaches 2 of this function? Now, we know that x squared, okay, so I'm supposed to draw x squared up until 2. So what does x squared look like? Remember, we've got like 0, 0, here we go, goes through 2, 4, goes through negative 2, 4, and you know, it's a parabola, so it kind of comes down like so, and then comes up, right? And sorry, this is something like that, right? And we're only supposed to draw it up until 2, which means that really what I did here was slightly wrong, right? I should have drawn an open circle there to indicate that at 2, 4, this function sort of stops. And again, how do I know that? I'm going to plug in 2. F of 2 is equal to 2 squared, which is equal to 4. So I know this function is going towards 2, 4. Now when I look at the other one, of course I plug in f of 2 down here. I get 2 plus 2, which is also 4. Except of course this one is a straight line with a slope of 1. So it starts right here, and then it just goes up and to the side like so, right? Like a straight line just heading up into the side. Okay? Now in this situation, you notice that the two sides of the function both exist and both approach 4. So if I say limit as x approaches 2 from the left of f of x, I must conclude that that answer is 4 because I can plug it into x squared and that's what I get. If I go ahead and plug it into the other instruction, once again, I conclude that it is 4 because if I plug in 2 on the bottom one, I get 2 plus 2, which is 4. And in this situation, the two limits do agree. So left-hand limit equals right-hand limit, and therefore the limit as x approaches 2 of f of x is 4, right? And the double-sided limit exists there, and it is no problem. Again, just to go back quickly to GeoGebra to sort of verify, let's practice writing some of these piecewise functions, because again, this can be quite useful. So if, okay, so then I got to type in 3 things. What do I want it to do? What is my condition? So x is less than 2. Then I put a comma, x squared. So I want you to draw x squared as long as x is less than 2. Now, after the next comma, I tell it what to draw otherwise. And basically, otherwise, I'm telling it to draw x plus 2. So once again, what does it do? It draws x squared up until 2, and it draws x plus 2 after that. And as you can see in the image, right, that the two sides here do match like we would predict here. And again, I can type limit f2, and it's able to tell me that that limit does indeed exist at 4 because it recognizes that the two sides are both pointing to the same value. So there's a good example of, like, you know, piecewise questions. What can they be like? Sometimes they don't line up, sometimes they do line up, how do you interpret them, right? Well, and basically all you're doing here is plug into the top, plug into the bottom, check if they're the same, right? Then nothing else to it. Okay, so it seems a lot more complicated than it is, I think. I really don't think these ones are all that tough. This one is the same sort of thing. So, notice that I'm being asked about the limit as x approaches 1. So, do I even care about all of this stuff that's not related to 1? The answer is no, right? I only care about the first and the second part of this, right? So for example, if I'm going to draw 3x, if x is less than 1, so here's 1, 3, I'm going to draw an open circle at 1, 3, and then I'm going to draw a straight line, with a slope of 3, something kind of like this, right? So there's my line, and it goes all the way to 1, 3, right? That would be the left-hand limit here. So the LHL is equal to 3. Now, when I go to draw the right-hand limit, which is this part, right? So 2x plus 1. Again, what do I have to do? I just have to sub in 1. If you sub in 1, you get 2 times 1 plus 1, which is also 3. Now, 2x plus 1 is a bit of a different graph. It has a slope of 2, right, instead of a slope of 3. But they both line up in the same spot, which means we're going to fill in that circle. And once again, the two limits will match, right? Let's write it out just to get the practice. Limit as x approaches 1 from the left of f of x is equal to 3. Okay? Limit as x approaches 1 from the right of f of x equals 3. And then I can say LHL equals RHL, right? Sorry, L, which is my test, and therefore the limit as x approaches 1 of f of x is equal to 3. And both sides agree that 3 is in fact correct. Okay, again, just a quick summary of this one. I think you're probably getting the idea by now. If x is less than 1, draw 3x, otherwise draw 2x plus 1. Now again, I know there's other instructions on this graph, but for the purpose of what they're asking us, we don't need them, right? We only need to know what's happening at x equals 1, and as you can see, they line up perfectly fine. Now, suppose we, just for the sake of argument, let's imagine we were interested, what's the limit as x approaches 2? So I'm going to go back to my instructions here, and rather than my otherwise, I'm going to say if x is less than 2, draw 2x plus 1, and otherwise draw regular x. Okay? And what happens now, now we've got the thing that they wanted, right? So before 1, draw 3x. Between 1 and 2, draw 2x plus 1. And then after that, draw just x. And obviously you can see here that this is not going to be, the limit is not going to exist if we were to check at 2, and the reason is very straightforward, right? Don't overcomplicate something like this. If you want to check if the limit exists at 2, right? Limit as x approaches 2. You plug in 2 here, plug in f of 2 there, plug in f of 2 there. Now, if you plug it into the second one, the answer is 2. If you plug it into the first one, the answer is 5. So, does the limit exist? Obviously not, right? The two sides do not match. So again, we could sort of like fix up our graph if you want. Not really super important for what we're doing, but you could improve our graph just by making it look like that. And now it has the 1, 2, 3 sections. And the limit does not exist at 2, but remember, the question was whether it existed at 1. Okay. Now, by far the most interesting question here is this one, where it says the limit as x approaches 3 of absolute value x minus 3 over regular x minus 3. And this is certainly a challenge, because absolute value is not something we've spent a lot of time with, and really, I think, for questions like these, like this is the question to practice for absolute value. Okay, so once again, let's imagine we had a left-hand limit, and we're going to do this a little bit differently than normal, because obviously, if we were to sub in, so here's let's just go through what the obvious problem is here. Okay, so the obvious problem is this: if I try to sub in 3, I get 3 minus 3 on the top, 3 minus 3 on the bottom, and I get 0 over 0, which, as you know, is like the typical limit question, right? This is kind of like a normal limit question. That's what I'm expecting. Now, the problem with this is when I go back and I go x minus 3 over x minus 3, how do I cancel that? How do I cancel absolute value on the top with regular value on the bottom? The temptation, of course, is to just cross them out and say it's equal to 1 and that my graph is equal to 1. But let's be a bit careful before we do something like that, okay? Because absolute value is like, I want to make sure I'm doing this right. How do I actually deal with absolute value? So let's try the left-hand limit. The limit as x approaches 3 from the left. Okay? Now imagine for a sec, okay, so let's imagine. Okay, imagine we are looking at a value that is a little bit left of 3. For example, 2.99. Okay? Now what would happen if I plugged in 2.99 into this function? I get 2.99 minus 3 over 2.99 minus 3. Now that doesn't seem so bad. Okay, so on the top I get negative 0.01, and on the bottom I get negative 0.01. Now here's where your knowledge of absolute value has to kick in. You can see that the top and the bottom are the same value, so when they reduce, they're going to reduce to 1. But the absolute value causes the top to become positive while the bottom stays negative, which means overall the left-hand limit on this picture is negative 1. So, if we were to draw this, so here's negative 1, and we go over to 3, and the graph looks like this, where it's a flat line that is approaching negative 1 on the left. If you're not convinced of this, try to sub in any other number you want. Sub in 0, and what happens? If you sub in 0, you get negative 3 over negative 3, but the top has to become positive. So you get positive 3 over negative 3, which gives you negative 1. Try subbing in negative 2. Negative 2 take away 3 on the top is negative 5. That becomes positive 5. The bottom is still negative 5, and once again you get negative 1. So it seems like no matter what we plug in on the left side, the value of this function is always negative 1. Now, on the other hand, if we approach the right-hand limit, right, if we look at the other side, we're going to notice a bit of a different behavior. Because if we say the limit as x approaches 3 from the right, we might want to test the number 3.01. And when you test the number 3.01, the fact that the top is absolute value has just become irrelevant, because both of them are positive, right? And this side approaches positive 1. So what happens when you go to draw this is it looks like this, right? All the values on the right are positive 1, and all the values on the left are negative 1. And of course, the conclusion is the limit does not exist because the left-hand limit and the right-hand limit do not agree. So we'll just write that down quickly. RHL is not equal to LHL. Therefore, the limit as x approaches 3 of f of x does not exist. Okay? Now this is a really important question to practice. I think the test will offer something fairly similar, but it won't really be like a wildly harder version of this, because we don't do a lot with absolute value, and I don't think it's fair to give like a super complicated absolute value question. But there probably will be an absolute value question, and it's worth reviewing this particular question for that. So again, I would suggest like a little star beside this one, thinking about a future test limit question. Very, very common question to get. Again, let's just draw it just to verify what we think we know. So I'm going to draw ABS for absolute value, x minus 3 divided by regular x minus 3. And what I find is, kind of what we predicted, that if you look at the left side, you're going to be at -1. If you look at the right side, you're going to be at +1. And of course, if you try to type limit F3, it can't answer, right? It can't answer because it doesn't know what to do, right? The two limits don't agree, so which one do you want, right? We can't give a limit. Okay, so all of this stuff with graphs, I mean, the first 3 questions hopefully are fairly clear. You're basically trying to test the one side, test the other side, see if they agree. In terms of the absolute value, you are actually doing the same thing. It's just you can't test the number directly. You've got to test the number that's nearby. Okay, so you can't plug in 3 into that, for example, because the top and bottom will be indeterminate. But what you could do is plug in 3.01, and then you know what the right side's doing, and you can plug in 2.99, and then you'll know what the left side is doing, and then you can give an answer based on that. Okay, and that's how you would deal with one of these absolute value type of questions. Okay, so really, really good one to like go back and study and try to do it on your own. And it's not that it's super difficult. It's just like there's a lot to learn in this first unit, and when you come to the test and see an absolute value question, you just want to make sure you've spent a little time on it and are comfortable with it, right? That it's not like, oh, I haven't done that since the 3rd day of class. I don't remember how it's done. Now, the final strategy for you, and I think by far the most important, okay, is the substitution strategy. And it's important because it is going to help you deal with problems that we just don't have another good way of dealing with. And the idea is we're going to try to take a question that is fairly difficult and try to make it into a form that is a little bit easier for us. And I think, if I remember correctly, one of the problems with the notes here is that both the questions are asking about when x is 1. So I'm going to try to find a question where x is not approaching 1 from the book. But we'll do that when we get there. So I'm going to do A with you, and then let's leave B for you to try on your own. It's pretty similar. Hopefully, once you've seen A, you can try B. But rather than do B, I'm going to pick a different one from the book that'll just show a little bit more detail about this, because I don't want you to think that like it only works when x approaches 1 or something like that. So when I say a substitution strategy, what are we supposed to do? So looking at this one, right? Clearly, if I were to attempt to plug in 1, which is, remember, always a good first step to try, we have 1 to the power of 1/6 take away 1 over 1 take away 1, which of course is 0 over 0, and 0 over 0 is indeterminate. It means I probably do have an answer, but I don't know what it is. I need to try to do some more work to solve it. Now, the issue with this one is that I don't have a rule for dealing with the power of 1/6, right? Like our conjugate works for square roots, right? Square roots, which remember a square root is like x to the power of 1/2, whereas a 6th root is x to the power of 1/6. I don't have a conjugate for this. Okay? In fact, you don't have not only do you not have a conjugate for x to the 6th, you don't even have a conjugate for x cubed. Okay? The conjugate only works for square root. Don't use it anywhere else. Okay? It does not work for anything but square root. The conjugate for cube roots and 4th roots and whatnot is more complicated, and we don't really need to go there. We're going to use a substitution strategy instead. So let's think about this. Can I factor this? No. Right? So just think to yourself. Can I factor? Nope. Can I conjugate? Nope. Is it a rational expression? Can I use a common denominator? Nope. Can I use the strategy from above where I draw it? No idea how to draw it, right? I have no clue what this would look like. I mean, obviously I can use a computer to do it, but, am I going to use that on a test? No. So all of my other strategies have failed, right? I can't factor it, I can't use a conjugate, I can't use a common denominator, etc., etc. So what do I do instead? So at this point, what you do is you introduce a new variable, okay? So, for example, this question would be a lot easier if x to the 1/6 weren't there. So I'm going to say let u equal x to the power of 1/6. Okay? And the reason I'm doing this is because I want to take something in my question that is difficult, and I want to write it in a way that I might be able to work with more easily. Okay? So you're going to say, you're going to take the part of the question that looks the most complicated, so this 1/6, and you're going to replace it with a different variable. Okay? So let u equal x to the 1/6. Okay, that's step 1. Step 2 is you are now going to isolate x. Then x must be equal to what? So look at your function, or your equation. U is equal to x to the 1/6. So I could get x isolated if I raise this to the power of 6 and raise this to the power of 6, right? So that means that x has to equal u to the power of 6. Okay? And this is a consequence of u being equal to the 6th root of x, then x must be equal to u to the power of 6. Okay, so that's step 1 and step 2. Now step 3 is you say, and as x approaches 1, u must approach what? Well, if x approaches 1, then 1 to the power of 1/6 also approaches 1, and u is the same thing as x to the power of 1/6, so u must also approach 1. Now, the reason I mentioned before about why I don't want to do both questions with x approaching 1 is because when x approaches 1, typically u also approaches 1, and that is a simplification of the process that we just want to make sure we don't fall into by accident. In this particular question, because as x goes to 1, u also goes to 1, that the limit in the situation doesn't really change. But I'll show you an example afterward where the limit does change. It doesn't make it any harder. It's just something we just need to be aware of. So now that we've made those 3 substitutions, we can write the question again. Limit as u approaches 1, and instead of x to the 1/6 take away 1 on the top, right? I'm going to replace that with u take away 1. And on the bottom, instead of regular x, I'm going to replace that with u to the 6th. Okay? And now I've got the limit as u approaches 1 of u take away 1 over u to the 6th take away 1. Now, it might not look like this is actually that much better a situation, but it is much more likely that you'll be able to answer it from here than from the way it started. Consider the following. If we think about u to the 6th take away 1, what if we imagine that as u cubed squared take away 1 squared? Then really, right, this is a difference of squares. The squares are u cubed and 1. So what if we were to do a difference of squares on the bottom? Okay, limit u approaches 1. Now the top is still u take away 1. The bottom, okay, u cubed minus 1 and u cubed plus 1. Okay, so what we managed to do there is take what looked like a very complicated 6th root, like no idea what to do type of question, and we've used a substitution strategy to help our other tools apply. Now, I'm going to do a 10 count here, and before I go on with the next move, and I want you to think, so the bottom has a difference of cubes on the left and a sum of cubes on the right. Which one should I factor? Now remember, when you factor a difference of cubes, right, you always get the following setup. The first bracket is the cube root of the first, the cube root of the second. The next one is the first squared, the two of them together, and then the second one squared. And the second one squared is always positive, right? So the point is, you copy the sign in the first bracket and reverse the sign in the second bracket. I'm just going to draw that u again because it looks like a 4. Now, if you said I should work on the difference of cubes, you're right, because the subtraction will go here, the addition will go here. Is it in my interest to factor the sum of cubes over here? I don't think so, because what I am trying to do here, remember, is cross those out. And once I've done that, I don't need to do any more factoring, because remember, my goal here is to plug in u equals 1, which I could not do any step previously, but now I can, right? Now I can plug in u equals 1 and things work fine. So let's write it out. Limit u approaches 1. On the top I have 1. On the bottom I have u squared plus u plus 1. And then I have u cubed plus 1. And now I can plug in 1 no problem. I just get 1 over 1 plus 1 plus 1, 3, and 1 plus 1, 2. So I get a final answer of 1/6, and that is the limit in that question. Okay, let's verify it, and then I'm going to do a quick bird's eye view of everything we just did before going on to the last one. So the question was, right, let's go back to the question here. So x to the power of 1/6, take away 1. Okay, so that's our numerator. And then x take away 1 as a denominator, right? That's the function. And you can see the function is sort of this weird looking, like sort of a root, but sort of like an asymptote at the same time, right? And that's that. Now, what is the limit as x approaches 1? Well, if we try to plug in 1 and f of 1, the function's unable to draw it. But of course, we know something has to be over here, right? Whatever this hole is, we should be able to locate it. If I type limit f and then 1, it will come up with 0.16666, which, remember, fraction, if I were to take that as a fraction, that fraction is 1/6, right? Which is the same answer that you and I came up with doing it algebraically. So this question is very, very important as well. Probably the most important of all of them, right? Where you're doing a substitution method, because a substitution method is guaranteed, right, to be on your unit test for for limits. So remember, with a substitution, you take the part of the question that looks the ugliest, right? The part that you don't want to deal with the most, and you replace that with a simple variable. So instead of x to the 1/6, let's call it u. Then you adapt your question that instead of working with x, you work with u. And once you've got it in terms of u, you'll find the question will work with one of the strategies we already know. So you can factor it, you can conjugate, you can common denominator, you can draw it, whatever. You couldn't do that before, but you can do it once you've made the substitution. And once you've made the substitution, you go through, you factor, you do the same old thing, and you get the answer. Okay? Now, the last thing I'm going to do here is I'm going to draw one of the questions from the book rather than this one. I think this one is a bit too similar. It's very, very good for you to try, but and I could take it up with you tomorrow. But let's do one of the ones that don't use x equals 1, and then we'll wrap up with this final drawing question. Okay, so here are some of the questions from the book. Question 8, okay, on 46. Okay, so question 8, evaluate the limit by using a change of variable. And again, a change of variable is what we were just talking about, right? It's a substitution type of strategy that we're going to use. So let's imagine, we want to look at maybe this, what would be a good one here? Maybe the first one would be good. I mean, all of these are good. Like, these are really good practice, I think. You'll notice, like, C and D are taken directly from here, right? They're the same ones we just did. But let's take a look at A, because, A will give us, like, kind of what we need to show. Just to show, like, what do you do if it looks a little bit different, right? So let's give ourselves some space, and let's try this limit. Okay, so once again, it's evaluate the limit using a change of variable. And this time, the question is as x approaches 8. So again, I'm going to kind of look at this and go, okay, so first of all, it tells me to use a change of variable. which, keep in mind, your test won't. Your test will just say find the limit, right? And that's something to kind of think about. Like, how would I even know that I'm supposed to use a change of variable here? And again, I would suggest if you try your other strategies, they just won't work. Like, what could you factor? What could you cancel? What could you... You can't use a conjugate because it's a cube root, right? Not a square root. So this is a trap some people will fall into, where they'll try to use the conjugate, but you don't use the conjugate if it's a cube root. So once again, you know, I know that I got to use a change of variable here because none of my other strategies work, right? I can't cancel anything. I can't factor it. I can't draw it, and I can't rationalize it. So, you know, what else can I do? If you plug in 8 on the top, right, you get the cube root of 8, take away 2, which is 0. On the bottom, you get 8, take away 8, which is 0. So unfortunately, it's not one of those lucky questions where it just works out of the box. We're going to have to do something to figure this out. What do we do? So my suggestion is take the ugliest thing in there and replace it with u. Let u equal cube root of x. Okay, that's statement number 1. We're going to let u equal the cube root of x. If that's true, right, if u is the cube root of x, then u cubed must be x, right? Because basically I just cube both sides, and then I can isolate x, and u is cubed. And finally, and as x approaches 8, u approaches what? Now, how do you do this, right? Well, think about it. If u is the cube root of x, and x is 8, is approaching 8, then u must be approaching 2. Okay? And that's how we know what u is approaching. As x is approaching 8, u must be approaching 2. Because u, right, is, you have to cube u just to become x, and hence you have to cube 2 in order to become 8. So now look how much easier this question looks like once I've made this substitution, right? Now it's limit as u approaches 2. On the top we have u take away 2. On the bottom we have u cubed take away 8, right? And that's basically like, that's a much easier question. That's a yesterday question, right? We don't need, like, the whole point of this substitution stuff is to take something you can't do and turn it into something that you recognize what to do with. Again, what are we supposed to do with this one? Is just take the difference of cubes on the bottom. The top is a u take away 2. The bottom, u take away 2. Then u squared plus 2u plus 4, right? That's your difference of squares formula. Again, we can cross them out. We get 1 over u squared plus 2u plus 4, and all of a sudden, the problem we've had all along, which is plugging in u equals 2, is not a problem anymore. And I find I get 1 over 12, right? 1 over 4 plus 4 plus 4. I can solve the limit. Okay, so this is, I think, these substitution ones are really important. They're some of the harder ones. They're definitely ones that you should spend time practicing. And that set of questions there at question 8 is exactly where you should go, right? So, you know, whatever it says here, like 46, number 8, and then it gives you a couple more at number 10, right? And that's what you're doing there. Now, the last thing for today is to just, it says sketch a graph with the conditions. This is, you know, it's almost always part of my test. I usually put it in the communication section to sketch a graph with conditions. It's you know, we're going to learn some more conditions before the unit's over, but just to get started with today, this one says, okay, we have to draw something where f of 1 is 1. Okay, so let's go over here and we'll draw a filled in circle at 1, 1. Then we say limit as x approaches 1 from the right is 3. So x approaches from the right. Now what does it do as it approaches? It doesn't matter. It could wave. It could do whatever you want. But it just has to approach 3. Okay? What else does it do is up to you. It doesn't matter. Just make sure it's still a function. The only way you can get this wrong, okay, is if you draw something that isn't a function. So don't draw that. because that fails the vertical line test, right? So you don't want to draw something that isn't a function, but besides that, you can literally draw whatever you want. I mean, like, you don't make it complicated. You don't have to make it wavy. Just make it a straight line, right? The limit as x approaches 1 from the right is 3. That my graph fulfills that condition. Does it have to look exactly like this? Of course not. It just has to point to this specific value. Then we're going to approach from the other side, except from the other side, we're going to approach 2. So I'm going to draw an open circle at 2, and on this side, how about we just draw a flat line, right? We can draw whatever we want, right? It doesn't have to be a line. It can be a function. It can be a wave. It can be whatever you want. Just make sure it's a function, right? Don't draw something that fails the vertical line test like that or like that, right? That loops back on itself. Now, when you're done one of these questions, how do I mark them? Does your graph do this? Yes. Does your graph do this? Yes. Does your graph do this? Yes. Does your graph break any rules? So, for example, a common rule that gets broken is the vertical line test. Now, does my graph break the vertical line test? No. Right? So, this if you drew this, you'd get 2 out of 2 on this question because everything there is perfect. All 3 facts are true and no rules have been broken. Now, this is all kind of silly with a question that's this simple because as we get more into the unit, of course, we'll learn more things that we can add to this before I ask you this question on a test. But it doesn't hurt to start thinking about this now. Draw something that fulfills each condition and draw something that doesn't break any of the rules. And for now, what are the rules that you could break? You could break the vertical line test. And a more common way that someone might break the vertical line test is they might fill in this circle. Right? And now you've broken the test because you're telling me that when x is 1, y is 2 different values, right? And it can't do that. So remember, if f of 1 is definitely 1, which is what the first statement says, that means the filled in circle has to be there, which means the other 2 circles have to be open, right? Because if they weren't open, you would fail the vertical line test and you would break the rules, right? That's the thing we need to avoid. So that concludes today's lesson on limits. There's some good practice work here that you can try. And again, bring the questions tomorrow, or feel free to post them to the site, and then we can take them up together. But for now, just keep practicing, keep trying to figure them out, and make notes where you're getting stuck. And let's talk about that. Okay, have a great day, and I will see you tomorrow.